Thank you all for being here. It's a pleasure to be in the MOOC. So I'm Malte Rötgen. I'm a late PhD student from Hamburg, from the group of Peter Schmeicher. I'm here for 6 weeks, so now it's 2 weeks left. And today I'm going to tell you a little bit about the topic of latent symmetries. The topic is divided into 2 pieces. First, I will give you something which you probably already have seen, like symmetries in one or other form, or local symmetries, as we call them. And then afterwards, I will give you a short introduction to latent symmetries. The talk is not meant as presenting only work, but it is meant like an introduction. So when you have questions at any time during the talk, just ask and I will try to answer them. So, well, it is always, there's only one person standing in front, and but the work has been done by many, many people. So especially, I mean, in Hamburg, those have been the former postdoc Christian Morphonius, who is now switched to industry and is working on LiDAR systems for self-driving cars. There's Maxime Pisch, who was there last week. He's a PhD student. And in fact, most work on the theory of latent symmetries, it was really an intense cooperation between Christian, Maxime, and me. Of course, Peter was also there, my supervisor. Then we also had input from Athens, Fotis Diakonos, who I think some of you know. And Nicholas Paleodimopoulos, I hope I pronounced this correct. I asked Christian, who is now in Crete. He was a former PhD student of Fotis. And then, of course, the reason why I'm here is I'm collaborating with Olivier, Vassos, and Yorgos, and Vincent, who is now still in the train, unfortunately. So we are working also latent symmetries in acoustics, and I'm going to tell you something about this project as well. And then we have also another side project. This is not currently of latent symmetries. It's about compact localized states, and it's related to flat bands. You will see this in a second. And this is Luca D'Alnegro and Fabrizio Scrinui. I hope I also pronounced this name correctly, from Boston University. So let's start. I thought I will start with a teaser. So at the end, as you will see during the talk, normally I'm working with matrices, but I thought, come on, let's not start this topic with something completely dry. So this is a picture of something which we have not yet submitted. It's a project together with Vincent Pagnon. And what you see here is just a simple two-dimensional setup. And then, well, shown is the specific eigenmode of the, a solution to the two-dimensional Helmholtz equation with, of course, non-boundary conditions. And what you should see is that overall, the system or the setup has no symmetries. So I invite you to check. I mean, let's say when I say symmetry, I mean, let's say invariance of the setup under reflection or rotation or whatever. What you can see, though, is that the upper cavity here, which is marked by my mouse, has a reflection symmetry. And then this cavity is coupled via 2 legs, left and right, over the points M1 and M2 to something which is not symmetric in the lower half. So normally, just by intuition, what you would expect when you couple something which is symmetric to something which is asymmetric, or I mean, which does not respect this symmetry, then the eigenmodes of this composite setup will not have symmetry. That's a normal intuition. And what you see here, though, is that this particular eigenmode has reflection symmetry in the upper cavity. And the reason for this is that there's a latent symmetry, and it's just a teaser now, but there's a latent symmetry between those points here, meaning that the eigenmodes in a specific limit where you take all these waveguides to be quite thin, they will have parity on this point here and that point. And in this particular eigenmode, even though we are rather far away from this limit, you see the waveguides are far away from being very thin. Well, you still have this parity, and as a result, the reflection symmetric cavity in the upper half, it does not see the asymmetry of the setup below. It just sees, well, it's connected over these legs, and then it sees a wave function which has parity. So at the end, as a result, you can have reflection symmetry in the upper cavity in an asymmetric setup. And yes, so this is, so to say, the final endpoint of this talk, but now let's try to get there. And yes, I said I work with matrices, so, but I also work with graphs. So how should I start? Well, normally, if I give this talk in front of some people, or people working with quantum mechanics, I would say that you all know the Hamiltonian operator. and it has an abstract form like this, a dagger and ace, I mean, all these operators. But what you can always do is you can go from your abstract operator representation in terms of, let's say, second quantization to a matrix representation. And if you have such a matrix representation, which is given here, it's just a toy model, so there's no, I guess, there's no real physical system behind this 4x4 Hamiltonian matrix. What you can always do is, for a square matrix, represent it graphically as a graph. And what you just do is you look for in each line and column, and you look for a non-vanishing matrix element. So here now I'm pointing to do it on the screen so that the people on Zoom can also see it. So here I'm pointing to the matrix element H12, and this matrix element is equal to 1. And now what I do, I go to the graph and I look at well, vertex 1, vertex 2, and there's a line between them corresponding to this coupling of 1. And now I just invite you to do this in your head. What you can also see is, this is another thing which usually graph theorists do, the diagonal elements of the matrix. If you think about, so let's say this matrix element H44, well, what does it do? It connects vertex 4 to itself. So at the end, what you get is loop. And this loop has the weight V, so the onset potential, and this is what you can see here. You can also, I mean, the matrix does not need to be symmetric. Here it's Hermitian. So when you, for example, look at the matrix element H23, it's 1 minus I, and H32 is 1 plus I, and this you can graphically represent by these arrows. I hope it's visible. Yeah. So I just leave this here for 20 seconds. And of course, so at the end, I always work with the matrix eigenvalue problem. So H times vector equal lambda times vector. And well, this is of course applicable to many problems in acoustics, like coupled mode theory in waveguides, or when you have granular media or spring mass systems where you have the Hessian matrix. It could also be applied to multiport systems described by a scattering matrix, or the slide before by, I mean, to systems, having thin waveguides. Are there any questions on this? So this is very, fundamental for the rest of the talk. Okay, I see no questions, then let me proceed. So just to give you an example, so what is shown here is a project together with Luca Dal Negro and Fabrizio Scagnoli from Boston University. They work in optics, and on the lower right inset, you see a small setup. It just consists of 4 dipolar nanoparticles, so just very small spheres. And well, those, well, I said they are dipoles, and they are coupled to each other. And the coupling, I mean, if you look at the scattering resonances of this 4 sphere system, you get, it's described by a so-called Green's matrix. I guess you are much more familiar than I am. And at the end, this Green's matrix, well, there are 3 degrees of freedom for each of those scatterers. So this Green's matrix has a dimension 12 by 12, because we have 4 scatterers and the 3 degrees of freedom, so it's 12 by 12. And what is shown here is a graphical representation of this Green's matrix. And then what you can see, so we have, each particle here, for example, particle 4, which has x, y, and z degrees of freedom. You see here there's a loop, meaning there's a diagonal element for x, y, and z of particle 4, and also for the others. And then each line here corresponds to a non-vanishing matrix element of the Green's matrix. So, well, you could, if you're really keen in looking at this, then you can already see that you can decompose this graph into 2 isolated subgraphs. So if you look closely, the z components of each particle, they do not couple to the x, y, z. So if you follow those lines closely here, there's this line, and there's another one, and then this one, but there's no lines connecting x, y to z. So graphically, you get the statement that, well, this Green's matrix is a block diagonal. Just that's one reason why I like this graphical representation, because when you now ask a computer to plot this, there are some routines, and it will immediately plot, give you 2 disconnected graphs, one with x, y only, and one with z. So sometimes, or let's say in most cases, it's much easier, rather than to work with a matrix, just to go, which is completely equivalent to the graphical representation in terms of the graph. Okay, so that's the preliminary remark. Then I start with the concept of local symmetries. And I guess most of you have seen this. So what you see is on the right-hand side is a so-called diamond chain. Diamond because it has this characteristic, well, in German we call it route. I'm not sure what's in English. So this square, put on the one edge. And on the left-hand side, you see the band structure. And what you can see is it's marked in red. It's a famous flat band, meaning that for all, well, the energy, it has the same value irrespective of this K for this big band. And now let's try to understand the origin of this flat band. When you look at the system, what you see immediately is that it is reflection symmetric, meaning that if you draw a line going through those white circles or vertices, you see that you can just reflect the whole setup about this line and nothing changes. So this is what I call a global reflection symmetry. Global because we do this operation simultaneously and everywhere in the system. And now, well, it will be important, but don't laugh at me. It's kindergarten. Let's make a simple statement that first of all, we know due to this reflection symmetry that all eigenstates of the system, or let's say eigenmodes, well, they can be chosen to have definite parity with respect to this operation P, which is just the reflection. And well, then, as I said, if you just go to kindergarten, so if you take a negative parity eigenstate and call this phi, and compute its overlap over one of these right sides, which I just call W, so one of those sides here, then what you can do is, first of all, you know, if you do the reflection operation twice, you get the identity, so you can just put the P squared side here. And then you know also that the right side, it sits on the axis of reflection. So if you perform P, the right side is not transformed at all. So what you do, you let P act once to the left, you get identity, and you get you can act P once to the right, and you know phi is a negative parity eigenstate, so you get a minus, and so you get this so overlap of phi with W is equal to minus this overlap, from which you get that all negative parity eigenmodes vanish on the axis of reflection. I mean, if I would have asked you 2 minutes ago, you would say it's trivial. It still is, but let's go further. So now I made a small video. I hope it works. Yes. So what you see is the comparison of two different reflection operations. And don't worry, I will let the video run once again in a second. So on the upper part of the video, you see the effect of a global reflection operation. So you really reflect all unit cells at once, which is demarked by a rotation. And this, the fact that this operation commutes with the system is represented by the fact that after the rotation, there's no visible difference comparing before and after. But what you can also do is you can perform a local reflection operation, meaning you just do this reflection within one particular unit cell and do nothing at the rest of the lattice. So let's go back. So here, there's this local reflection. And as you can see, just as above, nothing changes, meaning that this particular operation of performing a reflection operation only in one unit cell still commutes with the underlying Hamiltonian describing the system. Well, this is this operation is visualized here. And again, now we can play the kindergarten game once again, but the only difference is now the operation is maybe a little more difficult, or let's say unusual, because what we can do is, I mean, this operation P, which is now the local reflection in one unit cell, it still commutes with the Hamiltonian. We can play the exact same game. We know all eigenstates have positive or negative parity. We compute the overlap of this negative parity state with the other right sides W. And what we get is that this particular eigenstate here, shown here, vanishes exactly everywhere else but in this unit cell. It's not exponential localization what I'm talking about. It's really, I mean, if you do the eigenvector computation, it has a zero. Here, there, everywhere. Just, it does not vanish in a single unit cell. And there's a funny story. So there's one guy in South Korea, he's I think half German, half Russian. I think you know him, Sergei Flach. And he's very big in this flat band business, which is very funny because flach in German means flat. So he somehow found his destiny. And in the term introduced by Sergei Flach, this is a compact localized state. But compact because it has compact support, and it's localized, and it's this eigenstate, so that's why it's compact localized state. And now there's a very, well, for some setups it's easy, like this, and others it's not so easy. But there's a strong connection between compact localized states and flat bands. Whenever you have a flat band, you can make a superposition of your block states to get compact localized states. And whenever you have compact localized states in a translation symmetric setup, you get a flat band. And now, let's try to understand this connection, this very simple setup. What you can, oh, that's too fast. What you can do is you can, do this operation not just in this unit cell, but in this unit cell. So again, you would get an eigenstate which vanishes everywhere, but in this other unit cell here. You can do this here, there, and so on. So in every unit cell of the infinitely extended system, and what you get is an infinite number of eigenstates, which all have the same energy. So you have macroscopic degeneracy. Out of those compact localized states, you can then superpose them and build Bloch states, as you would initially do if you think about a translation symmetric system. And the result of this is, of course, a flat band. So that's a really, drastic impact of such a local reflection symmetry on the eigenvalues of the system. And well, this talk is not at all about flat bands, but just to give you some points, because I also wonder sometimes, well, what is interesting about a state which is compact localized compared to a state which has exponential localization? And well, there's one, there are 3 points out of many. If you're interested in more details, there's a very nice review paper by Lekem, Andrianov, and Flach. Set it down here. So the first reason is, of course, that flat bands are completely dispersionless. So the group-based velocity vanishes, and there's exactly no transport. If, however, you go to real system, because it's clear to everybody that it's impossible to produce a system where you have this specific symmetry and all couplings are the same. If you go to a real system, there will be, of course, perturbations. And the interesting thing about this is that any perturbation, no matter how weak, it can completely change the transport properties of the system. This is especially interesting if you go to quantum systems, where you maybe go from approximation of non-interacting electrons, where you may have a flat band. You introduce interactions, and then even very small interactions can lead to a rich phase diagram. So very interesting states. And the last point, but I'm by far not an expert, so I just read about this. It may sound counterintuitive because the flat band features no transport, but flat bands may be related to high temperature superconductivity. Just if you wonder, there's one reason. So there's, I don't know how this quantity is called, but there's one quantity related to the jump temperature of superconductivity. And in this quantity, there's something like 1 over the density of states. Now in a flat band, no, it's so in a flat band, you have an infinite density of states, and that's why it's people think that due to a flat band, the jump temperature may be drastically increased. If you're interested afterwards, I can give you some references. This is also, of course, disputed because there's not just one superconducting system, but many different ones. And as you know, it's a huge field. So, but for now, just keep this there. There are many interesting points about flat bands. Yeah, just to give you other examples, I think you have also seen them. So this is another setup here where you can have a flat band. So what is shown above here is just the unit cell. And then you have 2 different types of couplings, the solid lines and this dashed lines. And again, you get a flat band. Here's the diamond chain equipped with another coupling between those 2 sides. And again, you can see now it's the same diagram as before, but the non-dispersive, the dispersive bands are a little bit distorted and the flat band is shifted. So, which is also interesting because due to this coupling here, you can effectively shift the energetical position of your flat band. You can even make it the ground state. And then this is the checkerboard system, which I'm going to show you in a second. There are 2 flat bands. And now to complete this part, let me show you 2 other videos. Oh, it's pyroclonal checkerboard. So this is one particular operation. So what you saw was that we did a local reflection operation again in one unit cell of this pyrochlor lattice. Let me repeat it once. And well, now you're experts on local symmetries. So you know this operation commutes with the Hamiltonian because there was no visible difference before and after this operation. So you can again play the game. And then if you do really the arithmetics, then you see that there will be two compact localized states and thus two flatness. This is exactly what we saw. And just in case you wonder, you can, of course, come up with all kinds of crazy reflection operations. And this would be one which does not commute. Because before and after, so before it looked like something like this, two straight lines, and then you get this cross. And afterwards, you get just a cross here, meaning that this particular operation does not commute with the Hamiltonian. Okay, then in view of time, let me skip this other part and then go directly to latent symmetries. And so, as I said, the focus of the talk is not flatbands, but I wanted to introduce or to give you a little feeling about local symmetries so that you can, when you see visually a system, can immediately know, okay, are there symmetries or not? So what you see on the left, it's a very simple setup. Well, it's embarrassingly simple. There's a reflection symmetry, and due to this reflection symmetry, you will have, I mean, all eigenstates will have parity on U and B. Those two red marked sides. So this is kindergarten, and now go to something which is not kindergarten. The system on the right-hand side, first of all, it has no symmetry. So again, I invite you to see it would have a reflection symmetry over this line here if this nasty little side here were not there. Because it's there, if you again play this game and like in the video, you do this operation, you will notice that before and after this reflection operation along this vertical line, the systems do not look the same. So this operation does not commute, meaning there's no symmetry. But if you, and this, I mean, when I first saw this, it was really strange for me. If you now diagonalize this system, so again, this is, I mean, how many sides? 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. So there's a small matrix associated to this system. Let's call it Hamiltonian. And then if you diagonalize this Hamiltonian, you will see that all eigenstates have parity on U and B, on the two red sides, marked sides. And yes, at the very beginning, for me, it was very strange because I saw no symmetry. I was trained to look for symmetries. And well, I know from symmetry follows, well, parity or rotation invariance or whatsoever. I mean, you all know the game of group theory. But now I have something which has no visible symmetry, but still the eigenstates behave as if there was a symmetry. And yeah, it was a clear miracle. And now, I mean, there are different ways of showing why this parity is there. I decided to go the drastic way, to go to a so-called isospectral reduction. So the basic of this is in graph theory. There's this reference here, and as you can see, it's very recent, yeah? It's from 2019. There's an operation called isospectral reduction. Well, for physicists, it's just an effective Hamiltonian derived from subsystem partitioning. So let's go through this formula to make some sense of it. So we have our original system here in the above. And now this isospectral reduction tells us we want to have an effective model over a small, and gain a smaller system. And in order to get this effective model, we need to know where we have to reduce. So in this case, we reduce over the set of two sides S equal to U and V. And U and V are exactly the two sides on which we had this parity, this miraculous parity of the eigenstates. And then what we do here, according to this formula, so we have our full matrix H, which is 9 by 9 or 10 by 10. I'm now too stupid to count for some reason. 9 by 9. Okay, thank you. Well, sometimes when I'm nervous, I forget everything. So 9 by 9 matrix H, and then we have S is a set of two sides. So HSS is just out of this big 9 by 9 matrix. We take the rows and columns corresponding to U and V. So we get a 2 by 2 matrix as HSS. Then we do this. I mean, this is just one part, and then we do this other part here. So what do we have? We have H S S bar. S bar is the complement of S, meaning all other sides of the system. So S has 2 sides, so S bar is 7 sides. So meaning that this matrix H S S bar is 2 times 7. Yeah, because we take the rows corresponding to U and V and the columns corresponding to all other sides. Well, and I think now you understand what's written here. So this is E. I mean, it's a free parameter. It's an identity matrix. Then you have this HS bar S bar. So, I mean, it's a 7 by 7 matrix describing the complement Hamiltonian, so to say. We do the inverse, which of course is not always well defined. That's will be done in a second. And then of course you do this, the coupling between the 2 subsystems again. So HS bar S is a 7 times 2 matrix. At the end, the result is a 2 by 2 matrix, 2 by 2 because well, S was 2 sides. And it is depicted in this bit in case here. Now you see again why I like, or let's say love graphs, because from this picture, you can immediately see that there's a reflection symmetry, right? So those 2 loops here and there, they are the same, and then there's just line connecting them. So if you, when the system has a reflection symmetry along the horizontal axis, the entries are energy dependent. This has to be the case because when we go from a 9 by 9 system to a 2 by 2 system, in order to not lose spectral information or eigenvalues, you have to get an effective parameter. So now the couplings are energy dependent. This is written on the right-hand side. There's really the matrix representation of this graph here. So it's 2 by 2, and the matrix language, this is a bisymmetric matrix because it has symmetry along both the diagonal and the antidiagonal. And now you also see why this is called a latent symmetry, because on the left graph, or let's say in the left matrix, there was no visible geometrical symmetry. But on the right-hand side, you see, so we made this latent symmetry, which was already included, but not visible. We made it visible by going to this effective Hamiltonian. And well, then if you play this game, you can, well, this is actually the explanation that all eigenstates have parity. Well, to give you a pictorial explanation, when you go to an effective model and all eigenvalues of the original model are kept, so reduce over some sides, then if you have an original eigenvector, well, it's which has 9 entries, you reduce, so you just take the entries on the 2 sides U and V. And now, since this guy here is reflection symmetric, its eigenvectors are parity symmetric. And so you can play the game. I hope this is clear. It's not just feel free to ask. Yes. Yeah. But again, there's no visible symmetry on the left-hand side, but it becomes visible after this. Yeah. Ah, yeah. Sorry, that was forget. Yeah, isospectral, because whenever this this inverse here is well defined, let's say like this: whenever H S bar S bar, so the complement Hamiltonian and the original Hamiltonian have no eigenvalues in common, the spectrum of this smaller matrix here is the same as the original one. And the spectrum really is defined as, let me do this. So I have what this guy here. So you have for a normal eigenvalue, you have the equation H. So it's a determinant minus lambda I equal to 0. And now with our isospectral reduction, I now call it lambda, not E, and it doesn't matter. So the eigenvalues are defined as a solution to this problem here. And now, since the entries of this matrix are lambda dependent, you can immediately, I mean, it's somehow clear that you get more eigenvalues than the dimension. And then there's a mathematical statement that in most cases, the isospectral reduction and the original Hamiltonian have the same eigenvalues. Yes. Okay. Well, and now it becomes interesting. So beforehand, I showed you the isospectral reduction, and then, well, when I saw it the first time, I thought, okay, let's say somebody gives me a system with 1,000 sides, so Hamiltonian is 1,000 by 1,000. Should I really check all different isospectral reductions just to find this this parity? And the answer is no, you don't have to. There's a much easier way, and indeed, it can be shown that well, let's say for real symmetric matrices, so like the one which I showed you, latent symmetry of U and V is equivalent to this nice statement here, meaning you take the kth matrix power of your Hamiltonian H, you evaluate the diagonal entry UU, so the uth diagonal entry, and you compare it to the vth diagonal entry of this kth matrix power. And if this these two entries are the same for all k, then there's a latent symmetry. And now again, the statement comes, oh no, okay, I have to go to infinity. No, you don't have to, because there's a Cayley-Hamilton theorem, which states that if you have an n by n matrix, you can express the higher matrix powers, let's say h to the power n or above, you can express them in polynomials of the lower matrix powers. And then you see if you have this equation 2 fulfilled for h to the power 1 until h to the n minus 1, then it is automatically fulfilled for all k. So meaning in practice, if I give you a Hamiltonian and you want to see whether there's a latent symmetry, you just, in quotation mark, compute the first n minus 1 powers, check the diagonals for some coincidences. If you have, well, two sides U and V for which the diagonals match, then you have latent symmetry. And then you automatically have parity, which is interesting because you get statements about the eigenvectors of your system or your eigennodes without diagonalization, just from evaluating the matrix powers. And just to make things even more interesting, this equation 2 and also latent symmetry, because the two are equivalent, can also be linked to graph theory and to eigenvalue spectra. And the statement is as follows. You have our original Hamiltonian H, U and V have property 2, and now you constructed two graphs H minus U and H minus V. And the minus means you take away this particular side. So in this case here, U, take away all couplings to the side, and then you get this graph here. So it's 8 by 8, before it was 9 by 9. And if you compare those two graphs, well, they don't look the same, but they have the same eigenvalue spectrum, which is not visible at first glance. It can be proven mathematically, and the proof is not that difficult, but it's quite counterintuitive. And I personally find this really interesting because we have so many different things linked to each other. You have the parity of your eigenstates of, let's say, a non-symmetric system. Then you get equivalence to matrix powers, which we can also, well, there's a graphical interpretation, which I'm showing you in a second. So we have this. And then again, you can even make spectral statements about some subparts of the system. Okay. What's the time, say?
It remains 20 minutes.
Okay. In the way, I mean, when you have questions, please ask. So, yeah. Okay. Now, well, the topic of this talk is latent symmetries, and what is very interesting is that actually, when you have a reflection symmetric setup, it can be shown that it also has a latent symmetry, meaning that you do the isospectral reduction over the corresponding sides, you get a bisymmetric matrix or reflection symmetric setup, and you also got this nice equality in the matrix powers, this equation 2. But the reverse is not true. This I showed you. So this 9-side system, there was no symmetry, but we had a latent symmetry. So latent symmetry is a broader concept than normal symmetries. And this is something which we have recently shown. So I guess it's, well, it's a classical result. If you have a system and it has a non-abelian symmetry group, then you know from group theory that your system will have spectral degeneracies. It's a classical result. And now for the latent symmetries, it was not so clear at all in the beginning. But in this reference here, we have investigated, and indeed, it's the case, meaning that if you have a non-abelian latent symmetry of your original system, then automatically there will be spectral degeneracies. And now this, for me personally, was very interesting because, well, there's this obscure, so to say, statement when you have a system and it has no symmetries and you see a degeneracy, then sometimes you might call it accidental because you see no obvious reason for this. But at the end now, I showed you already some systems which have no symmetries, but latent symmetries. So it means that maybe, I mean, we have not investigated further, but maybe some systems which have degeneracies and people call this accidental. After all, they're not so accidental. They're just related to a non-abelian latent symmetry. And this is indeed one project. So at the moment, we have this idea of well, having conical intersections being related to latent symmetries at specific points in the Brillouin zone. Yeah, so this is also, I mean, if you have some ideas on this, I'm happy to discuss it. Popped up in my mind some month ago, but I had no time to this. But just one interesting application of this. Let's skip that part. That also, yes. So before I showed you this equation too, where you have this matrix power h to the power k u equal to h to the power k v, and I said there's a graphical interpretation to this, and yes, there is, and I'm going to show you now. What is funny is that for people working in graph theory, this is kindergarten, but for me as a physicist, it was completely new. And I'm going to show you by means of a simple example where the elements of your matrix are either zeros or ones, but you can completely generalize this approach to arbitrary matrices. But here for zeros and ones, it's easier. So the statement is now as follows. So we have our toy model graph on the left-hand side. It has 4 sides, meaning it corresponds to a 4x4 matrix H. And then we know that this matrix element H1, 2 here corresponds to connection between 1 and 2. Now, if you go to the second matrix power, let's investigate the matrix element h to the power 2, 1, 1, which is equal to 2. And the statement is now as follows. The kth matrix, the element ij of the kth matrix power corresponds to walks of length k between vertex I and vertex j. Now we have k equal to 2 because we have second power of h, and I equal to j equal to 1. So we look at the first diagonal matrix element. So now what we have to do is we have to count walks from 1 to itself of length 2. And a walk is nothing else what it sounds. You start somewhere, you go, and then at the end you end at some point. And the number of steps which you can take is the length. Steps is 2. So let's start. We have we start at vertex 1, and we have to start and end at this. And we have to take 2 steps. So since there's no diagonal element, so there's no loop, we have to go either from 1 to 2 and back, yeah, 2 steps, the first line here, or we can go from 1 to 3, first step, and from 3 to 1, second step. Those are the only 2 possibilities. And now if you just, that's a funny thing, you just sum over the number of walks, you get the element of the matrix. And this can be done in any matrix power, and also it can be generalized to, well, arbitrary matrices. The only condition is that they are square, so n by n. And let me leave this out. I mean, for me, it took some time to get this. So let me just leave this here for half or 1 minute to see, show you. Of course, if you have a big matrix and want to compute, let's say, the 17th matrix power, well, there will be a combinatorial explosion and you will not do this by hand. But it's just funny because for latent symmetry, we have h to the power k u equal to h to the power k v, meaning that there's the same number of walks from u going to itself compared to going from v, starting from v going to itself in all for all length. Yeah, I mean equation 3 here you can forget because I skipped the topic, but. So now what we have latent symmetries. We have a connection to the isospectral reduction or the effective Hamiltonian. We have a connection to the eigenvectors. We have a connection to the matrix powers, and we have connected this matrix powers to walks. And of course, you could somehow think of this or relate the matrix powers in terms to interference, right? I mean, if you think of a wave starting from here, if you do the time evolution e to the iht, then what you do is, well, you have the exponential of your Hamiltonian, and you develop it in matrix powers, right? Also, I mean, so meaning that the time evolution in a quantum system is related to walks, which is very interesting, for my opinion. So one idea of ours, but it's again, there's a huge list of points. One idea would be to really go and evaluate the Feynman integral and see, because there you have really, I mean, you have this different path and you have the integral. Maybe you can also get latent symmetries there. No, we don't know at all what to expect, but it would just would be funny to analyze. Okay, are there questions until now? Because otherwise I would go to acoustics. Okay. Yes. So what do we need to apply the concept to something well, less abstract? Well, we need the matrix eigenvalue problem. So H times X equal lambda X. H should be diagonalizable. And well, there are 3 examples. Well, we can have multi-port scattering systems. So H would be equal to S. This is one project which I do together with Olivier and Vassos and Yorgos. Then you could also go to spring mass systems or granular media, in which case you have the well, you have a generalized eigenvalue problem with 2 matrices. V is a Hessian, and M I think is a dynamical or mass matrix. It's diagonal. Well, you all know this trick. You just multiply from the left by M inverse, and then you get the normal eigenvalue problem here, meaning that you can also apply the concept of latent symmetries to spring mass systems. We also have done this. Imagine you have really a tabletop experiment of some masses coupled to springs, and then a latent symmetry would mean, for example, that the x degree of freedom of one mass is has parity to the, let's say, y degree of freedom of some other mass. Meaning, if you look at an eigenmode, well, everything will oscillate. But if you observe the x and y degree of freedom of those 2 masses, they will be in phase, or out of phase, but they will always have the same amplitude. What this is good for, I cannot tell you at the moment, but just find it interesting that you can have a system, no symmetries, but again, your eigenmodes or eigenvectors have these symmetries. Okay, and then there's also thin waveguides, and apologies. So I just have time to to show this particular setup. Otherwise, if there would be enough time, I would go into all. So what is shown here? So we have this, it's quite fun. It doesn't take much to get latent symmetries in a waveguide system. So what is shown here is just a simple setup of 3 waveguides. They all have the same length L, but different width, and they have the same thickness. Well, the eigenmodes of this setup are described by solutions of the continuous Helmholtz equation with Neumann boundary conditions. But if you assume that the individual width of your waveguides are rather small compared to the lengths, you can go to the low frequency limit, and you can actually map this continuous setup to a discrete generalized eigenvalue problem. Generalized, I mean 2 matrices A and B on both sides. I guess that you have seen this. Vassos and Yorgos, Olivier, you're also working on this, your SSH, and I guess Li Yang's talk last week was also about this, more or less. So if you have questions, I can answer, but for now, I will just assume that you've seen this once. The important point is that from the continuum with the infinite number of eigenmodes, you will get to a 4x4 matrix, discrete system. And the eigenvectors of this system are nothing else but the projection of the amplitudes of the eigenmodes on these junctions or waveguide endpoints. Meaning that if you have an eigenmode here with eigenvalue k, then when you project it, the amplitudes of those 4 points here, then you will get an eigenvector of the 4x4 discrete problem with eigenvalue cosine of k times l. And now the game is as follows. If you tune the 3 widths, those are the only parameters we have. If you tune them accordingly, you can get latent symmetries. And in this particular example, it's very easy. All you have to do is you have to say that the width of the first waveguide has to be the sum of the second and the third. Once you do this, you will get a latent symmetry between point 1, so the end point of this left waveguide, and point 3, meaning this junction. So all eigenmodes of your 3 waveguide system will have parity on those 2 points. And down here, I hope it's visible. I had to squeeze the figure a little bit. What you see is really a solution to the 2-dimensional Helmholtz equation. And what you see, it has negative parity on the point here and there. It's a little difficult to see, but on the right-hand side, it's easier to see. So there, what is shown, we have the first 7 eigenmodes with numbers here, and then we evaluate the ratio of the eigenmode at this point and the eigenmode at this point. It's x dependent. Okay, so yes, the ratio value you see when it approaches x equal to 2, meaning this point, you have +1 or -1. So all eigenmodes have parity in this system. And now, of course, we evaluated this. So let's say this discrete limit is well only well exact when you have all widths much smaller than the length. So you might ask, okay, what happens if we go away? And this is shown here in the plot. So this is the absolute. No, it's not that. It's really the value of the ratio for those modes here. So when the width is more or less equal to 0, you have exact parity, -1. And if you go away from this limit, and you see, even if it's 0.4 of the length, you get still more or less good parity. Meaning that this is some effect which is not, after all, so much related to the discrete nature of your approximation, but it's something that is hidden in your geometry, and you don't see this at first. When you take all the widths being much smaller than the length, then you can somehow make it visible by well, playing the game of latent symmetries, evaluating the matrix powers, but the effect is there. I personally don't know, first of all, what to do this. I mean, what is it good for, let's say, in terms of applications? But what I find really interesting is that it gives a completely new viewpoint on let's say, also acoustic systems. You have a continuous system, you have no visible symmetry, and in general, this means, okay, you just have to let the computer do the work. But now, with this admittedly very simple setup, we have the chance of getting a better understanding of the systems. And maybe in the second step, then use this understanding to steer, I mean, to control some properties which we would like to have. Okay, and of course, I mean, this is just a very the simplest possible setup. 3 waveguides is enough. And what you can also do is you can couple. So what is shown here, the subsystem A is our 3 waveguide system, albeit now not plotted on a line, but on this angle here. So we have 1, 2, 3 waveguides. And you can do the same game, meaning demanding latency symmetric points, also for a 5 waveguide system. This is shown here on the low. It's, I mean, plotted like this on a, like a snake. And so in the system A, 1 and 3 are latency symmetric. In B, 6 and 10, so the 2 green sides are latency symmetric. And then, well, it was not so easy to show after all, but if you connect those 2 subsystems A and B via the same waveguide widths, so symmetrically, the composite system will still feature latent symmetry on all points, meaning this is shown here. So in this composite setup, you will have latent symmetry on 1 and 3, meaning all eigenmodes have parity on 1 and 3. And it will also have parity on 6 and 10, the 2 green sides. And well, then of course, this is just a discrete setup here. Let's build a continuous version out of it. And this is shown here. And there you have the 2 wet points here and there. And you can see, well, of course, it's not exact because we have not infinitely small waveguides. But you see it's more or less fulfilled. So this guy is plus to this one. And here you have the same. And again, the game is there's no visible symmetry in this setup. But, yeah.
So some kind of so you have 4 by 4 matrix A, and B is some different matrix.
The 6 by 6.
And then this kind of tensor product, for the full system after, it keeps both latent symmetries.
Yes.
If something with some constraint.
Well, the constraint here is easy. You just connect them on the latent symmetric points. So here the points are 1 and 3, and here 6 and 10. And you have to do the connection symmetrically, meaning the waveguide here has to be the same as here. That's all you need.
This could be general, or let's say you take 2 latent symmetric matrices, and you find a good way to
yes.
keep the full latent symmetry.
Yes. So you can also have 3 or 4 or 5, an infinite number, whatever you want. Connect them together. Yes. So it's like a Lego principle. Yes, and well, now I come to the teaser, which I showed you in the very beginning, and I think also time-wise, it's time to end. What you can do is then to play the same game of coupling something symmetric or latently symmetric to the other system, but now go to the continuum, so go away from this small waveguide system. So before I had systems A and B, those are waveguides, and we knew in the limit of small width, it will get exact, described by this generalized eigenvalue problem, related symmetry, and so on. And here, what we have done, we connected really an extended system. So this reflection symmetric cavity over the two lag waveguides. And the secret is, of course, we connected this cavity to the two latent symmetric points, which I call M1 and M2. And of course, well, depending on the dimensions of the system, the solutions will not have exact parity. This will only be the case if the widths of the waveguides will be infinitely small. And to show you here, we have analyzed the first 12 eigenmodes. And what you see is the ratio for the first 12 eigenmodes on this point and on this, so the center of those two red circles divided over each other, and then take the absolute value. So we don't have plus minus 1, but we would just have absolute value equal to 1. In the ideal case, it would be a flat line, meaning that the effect would persist for any width that we can take. But as you can see here, some deviate rather strong and others are not. But around this point, it's still more or less, you have the parity. And due to this parity at that point here, it's very easy to show that also the eigenmode part and this cavity here will have reflective symmetry. Sorry, can you say again? Ah, okay. Sorry, that was not explained. So what I mean is, let me go back to the simple system. So I said there will be latent symmetry if the width of the first waveguide will be equal to the sum of the second and third. And now, let's say I keep the individual ratios between the waveguide width, but I make them overall smaller. So I apply a scaling factor. Let's say I scale them over a factor of 100. And then I look, what is the biggest width of those three waveguides? And this is W max. So I keep the latent symmetry, but I just do the scaling overall of the system. Is this clear? Okay.
The big figure with the W max is the largest cross-section you can see.
Yes, apart from the reflective symmetric cavity. Yeah. So I keep the latent symmetry conditions on the waveguide widths, but I just make them smaller or bigger. If I make them very small, you get exact parity. If I make them bigger, you get deviations, but still, I mean, if you look at this system, there's no symmetry, but still, even if you go here, it's still very close. Yes, so that's more or less all I wanted to show you. Well, there's further information. I just leave this here. Otherwise, this would be my last slide. So thanks a lot for your attention. It was really a pleasure speaking here, and I hope you have some questions.